Hello, hello. Hello, hello. All right. So hello, everybody. I'm John Stultz, and in what I hope is everyone's here OSPM tradition, we're going to talk about proxy execution. So, of course, I always want to say thanks to all of the great and amazing developers who have been working on this patch set before me. It's maybe a little foreboding that all these lines have continued on to other things, but I'm going to kind of keep persisting here as I can. Want to also thank the folks over here for all the help and review that they've done. It's been really appreciated. And really, I can't take a lot of credit for much in this patch series. So the big problem for us on the Android systems team at Google, and we would really like to be able to use CPU share throttling to be able to hit background tasks. When we do, it improves the average numbers, but we end up with these really big outliers. These are in milliseconds. That's 120 milliseconds, this example. And in this case, in particularly, it's particularly bad, but like, so up here at the top, we have the foreground task. That's kind of the important one. And then here's the throttled task. And in this case, we're delayed, basically waiting for the background task to release the lock, and it took 120 milliseconds. But in this case that I have here, it's actually been happening in like almost a steady state for a couple of times there. So we had particularly bad luck there. And that can cause just a lot of interruptions and janks. And especially, if you're dealing with 120 hertz, you're talking like 15 frames of being lost in this time. So this basically makes CPU shares unusable for a number of devices. They basically just stopped using CPU share groups. So proxy execution helps avoid this mutex cause priority inversion. You can see here, this is a bit of an eye chart, I apologize. But in this Perfetto graph, we've got, the foreground task running. It realizes that it needs a lock that's the background task owns. It basically will realize that it needs to do a cross CPU proxy migration. So it then waits it over to the CPU. And then basically will select this background task. And the background task will run, release the lock, and then the foreground task gets to run. And this, this whole thing took, I think, 16 microseconds start to finish in this case. It can be longer. Sometimes we have in this chart, you can see due to the tasks sometimes have their CPU shares to run. The one that's interrupting us can get run for a while. And so you can get, sometimes 4 milliseconds or the hertz granularity. But this is a lot better. And when we put these, two examples on the same chart, you can see this is way better than like we want. Again, this is all very similar to what I had last year. Since last year at OSPM, the patch series has really, I feel like progressed pretty well. I've been sending preparatory patches to the list for a couple months here repeatedly, kind of gotten some minimal review. I do appreciate folks who have provided feedback and tags. It really is great. For the rest of the series, at the moment, I don't have any known stability issues. So that seems to be working well. Thanks to Kipratik for doing some performance testing. Right now, the worst case sort of seem on the small side, so 3 to 5%. I need to go digging a little bit more there, but a lot of the larger performance regressions we were seeing earlier have been resolved. While there's no known issues, I am sure there are issues. So I would really love some really careful review, both for the approach and correctness. And so my big question here is really, how can I help move this forward? It's kind of feels like I've been pushing it up a hill a bit, so I don't know what to do next. Just for some more detail on the progress since last year, with the V4, kind of was working out how to add a little extra state to resolve the weight wound mutex circular references, so we don't end up there. For V5, I got really frustrated because the stability wasn't where I wanted it, so I tore the patch into lots of small pieces that I could iteratively kind of work on and dissect. For V6, we stabilized the sleeping owner in queuing. For V7, we went back to the try to wake up return migration path. For V8, we got to enable the optimistic spinning on mutexes, and this recovered a lot of the performance that was earlier problematic. V9's been more kind of dealing with edge cases and races, and V10 was kind of mostly just polish. Kind of just a quick overview of the whole patch set. So all I've been submitting right now are just these preparatory changes. So there's a handful. And this was suggested earlier because this is such kind of a big chunk of change that, I think it's hard for people to kind of really dig into. So just trying to get the little bits moving in first, and then we can start discussing as we go, is at least the strategy. And so as far as, that's the current set of what I want to submit. The next series would probably be the config option and the boot arguments so that we can turn it on and off at boot time. Then basically the task blocked on, which mutex were blocked on, and state tracking is the next chain. There's then the runtime accounting and the PSI fix-ups that deal with the split contexts. And then there's the initial find proxy task selects, find proxy task code, which doesn't actually do proxying, but just kind of gets us to the point where we're able to keep tasks on the run queue, and then basically deactivate them if we once we run into that step. And then we start kind of building on that, where we only proxy if we're on the local CPU, if the owner's on the local CPU. Then we add the waiter migration and the return migration, and then the sleeping owner and queuing and activation, and finally chain migration. As far as the current issues and concerns, yeah, the sleeping owner and queuing and activation is messy to me. At the moment it is, in the last revision, it's been implemented with some recursion just because that was easier to think through. I've just recently rewritten it to get rid of that, so I'm kind of chasing out any issues in that and making sure it's stable still. There's still a lot of potential races around trying to kind of, when we activate a task, having a list of tasks that we then have to go off and activate. But at that point, we've let go of the locks for the main task. And so it can start running and it can sleep. And then we might need to re-enqueue tasks back onto that task. And so it kind of gets into this weird, I've run into some weird live lock situations that I've had to work out. And so this one is messier, and I suspect is where any of the remaining issues are. So thoughts on how to improve that would definitely be appreciated. But at the moment, it does seem to work. The other issue that I've been looking at is the scheduling invariant for RT. And this is basically making sure that we run the top NR CPU priority tasks, those NR CPU that are out there. And in digging on this, I realized it's actually already broken. And so basically the RT push IPI feature basically opens this window where if we have a high priority task that then stops running, when we go to try to find the next highest priority task, we'll just say, pick a CPU, IPI it, tell it to migrate something, push to us. And then in the meantime, we go run the lower priority task. And so this is already kind of problematic. Disabling RT push IPI definitely improves it, but I still managed to find some edge cases with mainline, with running the lock torture test in the background, where I see failures. So I'm still kind of digging on that. And so as far as the situation that I'm worried about with the proxy execution, I haven't quite been able to contrive that situation to occur. So it's one of those things where it's potentially problematic, but it's already broken upstream, so I don't know exactly how important people feel this is. The other issue that was raised last year was concerns around the PELT estimation load caused by the block tasks being migrated. I've started to dig in there, but I also feel like at a philosophical level, it might not be the wrong thing to have those tasks included in the PELT estimation on the run queue. Because the idea is if you have a lot of waiters, we want to say this run queue is important.
So just for me to make sure I understand the way it's working. Yeah. So right now, when a task is blocked and unlocked, it's remain in the queue. That's the point?
Yes.
As a block.
It remains on the run queue. Yeah. And if the owner down the chain or wherever is on a different CPU, we migrate to that run queue.
But even before migrating, it's mean that it's how its PELT value are moving forward. It's mean that we are continuing to make like if it was runnable, even before the migration. That's even the other step. But even without looking at migrating, if the task is blocked, normally we should move the task in a sleep state, so its load will decay. Now it remain blocked, but on the run queue, which
Yeah.
means that the load will continue to increase.
But it's also going to be donating, right? So in a way, we're saying when your mutex blocked, since you're still on the run queue, we still want you to be runnable as a donor task.
No,
Exactly. It's the whole point of the scheme. So a mutex block task remains runnable and will donate its runtime to the blocked task.
To the owner.
To the lock owner, yeah.
yeah,
So-
but if it's not the task, I mean, if you have several tasks blocked, so you will take the execution environment of one, but the other one remain runnable.
Yeah.
So I
But
mean,
it's all pushing to block, to boost
yeah,
that task.
it just
Right.
yeah, I understand that. I understand that once you run in the context of someone, you have to increase. But these are the runnable, blocked, and not donating their execution
they-
context. They will still increase.
So they will all remain runnable, and they will all continue to build up lag, and eventually they'll all get their fair share of runtime to donate to the lock owner. Suppose there is four tasks. One hold the lock and does something for many minutes because it's really stupid. And then the other three, they sit there on the run queue waiting, and they'll each four of them get scheduled in round robin fashion, more or less, as expected. And then if the non-lock owner task gets selected, it will proxy down to the lock owner. And this way, you'll get the runtime of all four tasks contributing to finishing the lock region. So the weight accounting is absolutely correct by keeping it in.
Is it not the same kind of problem that you have with the delayed DQ?
We're not sure yet what delayed DQ does wrong for EAS.
Okay.
I have one proposal outstanding, but since that ARM guy is there in the room and he forgot to bring his Pixel phone, he can't test it. So we'll see next week. But fundamentally, keeping these tasks on the run queue and keeping their load on the run queue is correct. If
So
that
you mean
causes
that right now it's not correct in this case. That's what you mean. Right now, let's say that we have three tasks for one, or four tasks for one lock. The first one take the lock, and the other one won't take the lock as well, but they have to wait. So right now they are blocked in sleep state. They are no more runnable. So their load or runnable state is decaying.
right.
With proxy execution, they remain runnable. Then if the one that on the lock doesn't have the CPU anymore, but will give that to someone else, I agree that the one that will run need to increase, but it's also mean that the two other one are increasing the load and they're runnable.
Yeah.
It's a change in behavior.
It absolutely is a change in behavior, but it's what we want for proxy execution. You want to actually donate the time of all the tasks in the wait tree towards resolving the lock. And in order for them to donate their time, they have to remain runnable.
I understand that they have to remain in the run queue just from a load tracking point of view. That's my point. But
I guess the idea is
probably
that
need to see what will be the result. But yeah.
the weight of all those are kind of bearing down to say the importance of releasing that lock. And so they're all trying to push for that. So in a way, it is, I don't know. Yeah, it's the remaining runnable. I've got to see about that because it's still is shown as sleeping in the task state, but practically they are still on the run queue and contributing to load. Another issue that's not listed here that Yuri brought up at lunchtime that is actually pretty frustrating is that so while with proxy execution, when we have the donors, we migrate to the owner. And the idea is that when we migrate to the owner's run queue, they contribute to selecting basically the owner to run there, because we don't know if the owner would be able to run anywhere else. We don't want to migrate the owner because the affinities may prevent us from being able to do that. And of course, the donors don't actually run on that CPU. They're just migrated for the boosting. But with deadline, the problem is that the bandwidth calculations are all per CPU. And so once you figured out how much this task was allowed on this CPU versus a different task, you can't necessarily just migrate a waiter and donate its cycles from that other CPU on the second CPU. And so Yuri was suggesting that really what you want to do is do the migration the other direction in the deadline case, where you want to basically migrate the owner to the donor and run it within the donor's CPU and bandwidth on that CPU.
And can we have the situation where both have some CPUs excluding CPU sets?
Well, this is the thing that I'm worried about too, where it's like with that idea of.
Oh, I thought it was mainly that you can't migrate
because
it's a deadline.
Can go both ways, and both ways. Yeah. I tend to think that you don't want to essentially do the proxying if you are not allowed to. Yeah. So if either the owner or because you'll be essentially consuming bandwidth in places where you're not supposed to be consuming that amount of bandwidth.
Yeah. This does open up a lot of ugly problems, because since there could be multiple waiters on different CPUs trying to migrate one task, they can fight. And you have the problem of, if one of them can't migrate that task to it, what does it do? Do we try to run queue to pull something else out and run it in the meantime? Or, it's kind of ugly.
Yeah, it is. And well, my understanding of the theory is that if you select a potential donor to run, but the owner is actually already running on a different CPU, the theory says you want to deplete, so do a while one spinning on the potential donor. Of course, we cannot do that. So yeah, I guess the implementation alternative would be to let someone run on the CPU while depleting the runtime of the potential donor.
So the most egregious example would be two partitions and a lock that is crossing the partition. I mean, that happens. I mean, the kernel is a shared resource, but theoretically and fundamentally, they are two separate pools of bandwidth. So crossing that divide makes absolutely no sense, but you have to do something. You cannot just let it be. So I'm not too worried about this particular issue. And I think migrating towards the owner is still the simplest option for all of that. I mean, all of that migration stuff is a giant headache anyway.
That is true. Yeah. The only, I think, problem if you migrate the donors to the owner CPU is that for deadline, again, you are consuming essentially you're moving bandwidth while you're migrating the donors. So you might be impacting other deadline tasks that are not part of the log change, because you're essentially using more bandwidth on the CPU of the owner that you are essentially not supposed to.
Yeah, but that comes from the whole logs thing anyway.
Yeah.
Left way or right way, we need to finish that log section.
No, just adding, it's more than the bandwidth, it's the bandwidth with that deadline. Because the deadline will be shorter, so you added even more pressure, like more utilization. And
yeah,
it's not only the bandwidth, it's the bandwidth because of the shorter deadline. So it's always worse than the declared bandwidth.
I admittedly do not have a lot of expertise in deadline, so it's one of those things where I'm going to have to try to think about this a little more.
Yeah, well, he has.
Yeah. So if I'm understanding the problem, because which I've been told maybe 3 times in these 2 days. So you have, say, one processor A and one processor B, right? And you have a task deadline running on processor A, which has runtime but locks, so it has to wait. And you have which is locked by another task, which on processor B, which is holding the lock but has no bandwidth, right? Both are deadline, yes. So I think, but I don't know. So I think that, and you cannot migrate, and affinity prevents you to put together on the same core. That's the case. The problem, because if you can migrate, if you can put them together, donating bandwidth has no theoretical downside, right? So because if you can migrate, put them together, and one don't donate bandwidth to the other, and so you do plus, minus.
You might have transitory problems. You might have transitory problems by doing that because you have the deadline.
Yeah, yes, but I think that you're worried about that is even worse than transitory problem.
Yeah,
right?
but the point is that it also generalized to the fact that you can have 2 tasks that cannot run one on the CPU of the other, and that's the main problem.
Okay, so
Disjoint CPUs.
So let me just think loud. So why doesn't the task holding the lock consume the bandwidth, the scheduled deadline bandwidth, by some other task which is in the same CPU? Oh, okay. And then you give it back after the lock is released. I don't know.
Yeah, that was also I was thinking of, but it's not what the current implementation is doing, and it might be tricky in practice to do this recursive thing until you find something you can actually be run. Yeah, and also you probably need to synchronize. I mean, this is a kind of simple example with 2 CPUs, but imagine you have n CPUs. It might be tricky to do the synchronization properly, and there is.
Yes, since the algorithm is fundamentally graph, and in the case where we cannot migrate, can't we just use the reclaiming feature of graph, for example, to execute a bit longer and hope that
no, it's not. It's not the problem of finishing your deadline and then try to use reclaim to continue running. You want to donate also the deadline.
Yeah, but you need a way to give more bandwidth to the owner, no?
No, but it is not to give. The problem is not to give bandwidth. It might be the case that task is grabbing a lock with a full bandwidth, so it's not a bandwidth problem.
Okay.
The problem is that you need also to give the deadline, and then if you give the deadline without your bandwidth, like you can have a utilization higher than 1.
Yeah,
you see those things. These are the deal. The main, we talk about bandwidth, but the main problem is donating the deadline.
Yeah. Okay.
And then you can have like.
So, so far this problem, it does not affect the RT and SCADA cases. So it's one of those things where it's a little frustrating just because this was such a pretty generalized solution initially. And so now we're kind of running into the situation we're trying to figure out, that directional stress is hard, because definitely for SCADA or RT, you can't have cases where if you couldn't migrate one way, you just don't do it because RT tasks would not let go.
A way of using words to work around the problem would be a task cannot migrate because of preemptive disable, but if you are RT, you'll be using preemptive RT, so it should be short. Then the other case is migrate to disable, and we can use almost the same argument. Then
you're not always using preempt RT for RT tasks, though.
Yeah, but we would like to, but we are RT.
Oh, I'm right. Okay.
I know you don't have.
Yeah, I just want to make sure that
for the RT, where this would be much more of a problem.
Okay.
Right, missing the deadline on the RT would be much more of a problem.
Sure.
So, and then we have migrate to disable, that now they can be long, but we could work on the kernel to make them shorter. Yeah, because it was burned actually. The reason we get migrated disable is to not to.
The whole point of migrate disable is that it can stay locally CPU without disabling preemption and without changing affinity on the fly. And those sections can be, versus preempt disabled sections, can be comparatively long.
Let's say that we would agree on working to make that smaller.
Yeah, but
in the future, can we assume that?
Kinda, yeah, but I mean, we want to reduce locale section in general, but I mean that's a fight against windmills.
A migration RT patch set.
That's a fight against windmills.
But then we have the problem of not having disjoint set of tasks with deadline, tasks that cannot run on the other CPU. We could point for misconfiguration just to find an argument to justify the current algorithm. But see, it's one argument on top of the other.
Yeah, but I mean, you always will have to deal with the problem that tasks can't migrate independent of migrate disable. Have pin tasks which have the same problem.
Yeah, the thing that you and I were talking before, like, is that migrated disabled and preempted disabled, it's our problem, like in the kernel side, because it's not a user decision. But affinities are a thing. So.
Yeah, but the problem is that, I mean, if you look at real world, real-time systems, they often very consciously partition the CPU space for various reasons.
And makes the worse. Because the tasks are usually taking locks inside the kernel.
That's the problem, because they care about the isolation properties of being alone or only with a very dedicated set of threads on a particular CPU. But then the stupid kernel comes along and provides shared resources again and ruins everything. Yeah, and so you have to rewrite the kernel.
Yeah, and that's the point in the current proxy execution. You would donate the deadline, the absolute deadline of a CPU that is not yours. So that deadline doesn't belong to the CPU you are running. And then you would making isolation, it makes the problem even more apparent.
Yeah, of course, but we have to find a solution to deal with that.
Yeah, that I was trying to raise the cases to figure out which exception, because we would have to do some conceptions here. Otherwise, we will.
I mean, what?
Otherwise, we have been locked ourselves on this for quite a while.
I would still do that for the scatter T tasks. This direction of migration still works. You don't ever run the donor.
Yeah, no. For the FIFO scheduler, it's okay.
Right.
It's for the same reason why the priority inheritance doesn't have the problem of deadline inheritance.
Yeah, so that's.
Yeah, the problem is the bandwidth and the absolute deadline that doesn't belong to that CPU set.
The other thing I might want to try to push a little bit too is that if we can find a way to partition some of this problem space, because the needs that we have are definitely.
And that's what I was trying to raise the use case.
Yeah. Oh, yeah.
Blocks it, so we could say, okay, which one we can okay.
Yeah.
But in Italian, I'm saying it is what it is. But the problem is that the systems are generally partitioned and make the hard case even more apparent.
No, yeah, but if you partition systems, you still can have something. It's just a totally stupid brain dump idea. You can have reserved space on each partition CPU and utilize that one.
Yeah, but that's the thing. But still, you have the deadline.
Yeah, of course.
It's not only bandwidth; it's the absolute deadline. But that we could also say, we can also blame user, right? You should not have a shared resource between two CPUs that you cannot.
But that's hard for the system configurator because he doesn't know what
about the kernel,
what tons of shared resources are in the kernel.
And then we reach to the conclusion that I also have. We are deadlocked in the exercise. I was playing against myself.
I'm still convinced that number of CPUs equals 0 is the right solution for everything.
No, but we will lose our jobs. We need computers.
No, we could do fancy things.
So I might run through a couple of things from last year that we talked about as well. So one idea was this migration avoidance idea, where basically if we could run down the chain and check to see if the owner was running, then just spin and never do the migration. And that would kind of simplify things. One of the problems that we have with that is that there's alternation between tasks and mutexes in these chains. And we've got a lock for each of these that we have to kind of take. And so just by the locking order, we have to kind of take and release and take and release. And there's no way to keep this stable. The way that we do keep this stable is that we're on a run queue. And so we hold the run queue lock, and so the task can't disappear from us as we release the locks. And so that basically limits us to be able to see one task off the run queue. And that's as far as we can go. So there's no way to really know if the owner way down at the end of the chain and on another CPU is running right now or not. There was another discussion around kind of using this virtual run queue or chain container idea. So we could avoid doing the migrations and we could just migrate one kind of placeholder for the entire group. But the problem with that is that we can run in this case of, if we're not using a run queue, we need some container structure to kind of keep everything stable. And when you start to, block on another container, then you have to basically join the containers. And we can also have mid-chain wake-ups. And so you have to split the containers. And at this point, it's just going to be like a lot of mess to kind of keep track of something that devolves down to being the mutex wait list potentially for each case. So it didn't really seem like it was going to be usable.
That's another phase of the problem that we were discussing, but it becomes also visible when you think on bandwidth for the CFS.
Okay.
It's just that's more apparent on the deadline.
Yeah. Okay. I have to think some more. Yours just still needs some thought.
You see, I'm trying to find the excuse to accept the thing as it is, but I'm playing against myself here, just to be clear.
So as far as next steps, I'm going to continue to push the prep patches upstream. If anyone has any feedback on the strategy there, if people are thinking I really need to go with a different approach, I'm open to all of that. I've already taken a stab at getting rid of the recursion on the active sleeping owners, or activating sleeping owners. Spend some more time on the performance tuning and correctness testing. This is one of the areas I really wish there were a lot of more scheduler correctness tests. There's a lot of frameworks for making scheduler tests, but there's not a lot of established, find where I'm broken without having to, think of all the cases that I might be broken. And so particularly around deadlines. So if anyone has suggestions for good workloads to stress.
We can make runtime monitors of the status of the task using the status of the locking. That's easy. This is kind of easy monitor.
Yeah,
it doesn't involve no linear things, just discrete things. It's easy. We can make.
But really, can we get standardized test cases, please? Finally, we are debating this for decades now.
ELISA people.
No, but for scheduling, it's every time I try to do something and I'm scrambling to find something where I can compare apples with apples and not end up comparing random stupid workloads with random numbers generated out of them, which tell me nothing. I mean, we have, especially for stuff like deadline, you have a very well-defined semantics. So you should have very well-defined test cases for it to validate that this actually works and this actually does what it claims to do. So pretty please.
Yeah.
For deadline is easier because you have the semantics, right? For me, I find even hard to regressions on the fair scheduler. Like now with the TL server, I don't know what to run to see if I'm editing regressions on the fair scheduler.
Yeah, I mean that's but we do not even have test cases for the well-defined stuff. So basically we have nothing. So we have some kind of functional tests whether stuff the interface works, but really well-defined runtime test cases we don't have, and please can we create them?
I've really been enjoying going back to the LTP real-time tests and getting to get that SCED football test going again after 18 years. And so that's one of those.
We need
dive back in those old things.
We need to buy chocolate for this kind of conference. At least we have some kind of happiness.
Yeah. And then, basically pushing these patches at the pace that maintainers like. And so it's one of those things where I'm happy to kind of move slowly and make sure these things are sort of slow and iterative and stepwise, because I know there's a lot of complexity, and I definitely don't want to be dealing with a big chunk of change and finding that something's wrong and having to chase it down. So doing it kind of slow, I'm very happy with. I just want to make sure that we are in a space of being able to move forward. And then stuff for the future work, abstracting the block down pointer to apply to more than just mutexes. And then seeing how to connect to mutexes and replace RT mutexes. So I think please review.
Don't cry.
Yeah, please review. I don't want to scream into the void anymore. Yeah, so that's kind of it. I've got a couple other little, I don't know how much time, because I feel like I'm at time almost, or I didn't know how far over I went, or we started late, so. Okay, I can go through some of the interesting trouble with the sleeping owner and queuing if people care about that. If folks want to talk more about the deadline stuff, we can do that too. I just want to make sure. Okay. So one of the issues I had last year was this issue with weight wound mutexes, where I kept on getting to this case where we had these circular block down problems. And this was able to be solved with just adding a walk through it. You end up with a task that basically tries to get the lock and says the weight wound mutex wound. And so earlier I had this problem where I didn't have enough state in order to recognize that we had gotten the wound and we were runnable, and so we needed to let that task run to release the lock. And so it could then be executed and then solved. So that's kind of just a little background on that. For sleeping owner and queuing, we have this case where basically we have a task that's blocked on a task that's sleeping. And in that case, there's nothing you can do. You can't migrate it to boost it anywhere because it's just not runnable. And so what we do in this case is we basically add it to a blocked entities list on the task, and while it sleeps. And then basically once this task wakes up, we'll basically enqueue that task to the same run queue that task the owner wakes onto, so it can be boosted there. And so we can run into this case where you have multiple tasks in the chain on this kind of long situation, and they're all kind of enqueued on this sleeping owner. But task one tries to grab this lock 2, and we get a weight wound mutex wound. And so this gets an deadlock, and so we've got to re-enqueue it. And then at that point, it basically will run and release its lock, and that gets passed over and everything's working well. The trouble is we can run in this case where we get the weight wound mutex, or the weight wound mutex wound, at the same time this task is waking up. And then we run into a case where we get the deadlock, and then as we're trying to enqueue it, we end up trying to send it to 2 run queues at the same time. And so this ended up being ugly to sort out, and ended up I just needed to basically, on the activate blocked entities, I needed to take the task PI lock. But that is the topmost lock in the order. And so you have to let go of the run queue lock, you have to let go of all of the locks basically to retake that. And so it becomes particularly messy. And so this, I did manage to get through this, but it's one of those things where it does make the code kind of ugly to get through, because there's just a lot more races since we're letting go of a lot of locks in order to serialize where we're actually sending that task. So in those cases, since you let go of everything, you have lots of weird behavior where the task you were sleeping on may run for a second and then go back to sleep, and so things start getting re-enqueued onto it, and it's been kind of messy. So if anybody has thoughts on the thing I've been looking at with the blocked entities list, is it's kind of similar to a wake queue, but instead of, you're not actually wanting to run through the try to wake up, you're just trying to activate the task. And so I'm trying to kind of see if I can make some more parallels to that logic to make it a little cleaner. But if anyone has feedback on that area, I would love some review on that patch. I think that's it. Yeah, the rest of it's all background. So anything else? Any feedback at all? Into the void I yell. Ah! Okay. All right, well, thank you. Oh, Peter?
Yeah, no, I was gonna say that I'll try and have a look. I
I
know I've
appreciate
been
it.
really spotty of late. Shit happened.
Yeah, understandable.
But yeah, I'll try and have a look at the latest. I see the series in Git is complete. It has these annotation commits. I've not seen those before, but
Oh, sorry.
funny. No worries. I'll manage. So yeah, I'll try and have a look.
All right, I appreciate it. Thank you so much. All right, with that, thank you, everybody.